Learning objectives. In this chapter, the user will learn the following in detail. Vertex cover, the traveling salesman problem, approximate algorithms, scheduling problems, set cover problem, bin packing problem, polynomial time approximate schemes, basics of parallel algorithms, Flint's classification, SIMD algorithms for simple problems, list ranking, basics of randomized algorithms, GCD algorithm. Approximate algorithms. One way of dealing with NP completeness for optimization problems is to use an approximation algorithm. Such an algorithm typically runs much faster than an algorithm that strives for an exact solution, but it is not guaranteed to find the best solution. In this section, we study methods for constructing and analyzing approximation algorithms for hard optimization problems. The general situation is that we have some problem instance X, which would be an encoding of a set of numbers, a graph, etc. In addition, for the problem we are interested in solving for X, there will often be a large number of feasible solutions for X, which define a set F of such feasible solutions. We also have a cost function C that determines a numeric cost C of S for any solution S belongs to F. In the general optimization problem, we are interested in finding a solution S in F such that C of S equals op equals min of C of t such that t belongs to F. That is, we want a solution with minimum cost. We would also formulate a maximization version of the optimization problem as well, which would simply involve replacing the above min with max. To keep the discussion in this section simple, however, we will typically take the view that unless otherwise stated, our optimization goal is a minimization. The goal of an approximation algorithm is to come as close to the optimum value as possible in a reasonable amount of time. Provide a guarantee of how close an approximation algorithm comes to the optimal value. We say that a delta approximation algorithm for a particular optimization problem is an algorithm that returns a feasible solution S, that is, S belongs to F, such that C of S less than or equals delta opt for a minimization problem. For a maximization problem, a delta approximation algorithm would guarantee opt less than or equals delta C of S, or in general we have delta less than or equals max of C of S by opt by C of S. Construct delta approximation algorithms for various values of delta. We begin with the ideal situation as far as approximation factors are concerned. Basics of parallel algorithms. Parallel models of computation. Extending the RAM model to allow for multiple processors gives rise to a parallel model known as the Parallel Random Access Machine or PRAM. This is the synchronous parallel model in which all processors share a common memory. Because of its conceptual simplicity, this model seems to be a model which almost all parallel computers emulate in one way or another. The PRAM model is also well suited for discovering the inherent parallelism that may be present in a problem. Finally, the PRAM model seems ideally suited for finding general paradigms which can be used to develop efficient parallel algorithms. Parallel efficiency. In the sequential setting, we say that an algorithm is good if it has a running time that is at most big O of n power k for some constant k, that is, it runs in polynomial time. A problem is considered tractable if there is a polynomial time algorithm that solves it. In the sequential setting, once it is known that a problem can be solved in polynomial time, the goal shifts to finding an algorithm that solves the problem as fast as possible. Likewise, in the parallel setting, once it is known that a problem is in NC, the goal shifts to finding an algorithm that solves the problem and minimizes the product T of n into P of n in the asymptotic sense, where T of n is the time complexity of the algorithm and P of n is the number of processes used by the algorithm. NC stands for Nix class is the set of decision problems decidable in polylogarithmic time on a parallel computer with a polynomial number of processes. That is, if sequence of n denotes the sequential running time to solve a certain problem, then we want T of n into P of n to be as close to sequence of n in the asymptotic sense as possible. This goal is motivated from the fact that a single processor can simulate the computations of P of n processes by performing a step of each in a round-robin fashion. A parallel algorithm is optimal if its T of n into P of n product matches the sequential lower bound for the problem it solves. Technically, this definition allows a sequential algorithm with P of n equals 1 to also be an optimal parallel algorithm. So given that T of n into P of n is close to sequential of n for some problem, the secondary goal is to minimize T of n, the running time. The motivation for these two goals is that any existing machine with say k processors, a constant, can simulate an algorithm that is efficient in this sense to get the maximum amount of speedup. The k processors can simulate each time step of the P of n processors in ceiling of P of n by k time by having each of the k processors perform the work of ceiling of P of n by k processes. This approach results in an algorithm that runs in big O of T of n into P of n by k plus T of n time. In addition, any lower bound for the sequential running time necessary to solve a certain problem immediately becomes a lower bound for the product T of n into P of n because a sequential machine can simulate a PRAM algorithm with these bounds in big O of T of n into P of n time. Versions of the PRAM model. There are basically three different versions of the PRAM model, each differing from the other in how it resolves memory conflicts. The most restrictive version is the exclusive read, exclusive write or EREW PRAM, in which no simultaneous reads or simultaneous writes are allowed. If we allow more than one processor to simultaneously read from the same memory cell but still restrict concurrent writes, then we get the concurrent read, exclusive write or CREW PRAM. Finally, if we allow more than one processor to simultaneously write to the same memory cell, then we get the most powerful model, the concurrent read, concurrent write or CRCW PRAM. The method of resolving write conflicts varies, but the two most common methods are based on defining the model based on one of the following rules. Restrict all processors writing to the same location to be writing the same value. When k greater than I processors are writing simultaneously to the same location, allow exactly one of these processes to succeed arbitrarily. As an example of a CRCW PRAM algorithm, suppose we are given a Boolean array A and asked to compute the common OR of all the bits in A. Initialize the output bit O to 0 and assign a processor to each bit in A. Then we can have each processor assigned to a bit, that is, write the value 1 to output bit. This simple algorithm allows us to compute the OR of n bits in big O of one time using n processes in the CRCW PRAM model, using either of the above rules to resolve write conflicts. Simple parallel divide and conquer. The parallel divide and conquer technique is the exact analog of the classic sequential divide and conquer technique. The approach is as follows. Given some problem, we divide the problem into a small number of sub-problems similar in structure to the original problem, but smaller in size, and then solve each sub-problem recursively in parallel. In order to have an efficient algorithm, we must then be able to merge the sub-problem solutions quickly in parallel, once the parallel recursive call returns. As an easy example of using this technique, consider the problem of computing the sum of n integers. The same technique works for any associative operation. Let us assume that the input is an array containing the n integers and is already resident in memory. For simplicity, let us also assume that n is a power of 2. Divide an array into two subarrays comprising n by 2 integers each and find the sum of the integers in each subarray recursively in parallel. After the parallel recursive call returns, we can compute the sum of all n integers by adding the sums computed from each subarray. Since this can be done in big O of one time, the time complexity T of n satisfies the recurrence equation T of n equals T of n by 2 plus c, which implies that T of n equals big O of log n. The number of processes P of n needed for this computation can be expressed in the recurrence equation P of n equals max of 2p into n by 2, 1, which has solution P of n equals big O of n. Note that the T of n into P of n product in this case is big O of n log n, which is off by a factor of log n from optimal. Sequential subsets and Brent's theorem. The sequential subsets technique and Brent's theorem both involve constructing an efficient parallel algorithm from existing algorithms, which may not be very efficient themselves. Sequential subsets technique. The main idea behind this technique is to perform a limited amount of sequential pre-processing on small subsets of the problem to be solved, and then apply a parallel algorithm to finish solving the problem. In some instances, there may also be some sequential post-processing that needs to be done on each subset after the parallel algorithm completes. We illustrate how this technique could be applied to the n integer summation problem. First, we would divide the array into n by log n subarrays of log n elements each, and assigning one processor to each subarray. Sum the elements of each sequentially. Then we would apply the parallel divide and conquer procedure to sum the n by log n partial sums just computed. The pre-processing step would run in big O of log n time using big O of n by log n processes, as would the parallel divide and conquer step. Thus, this would result in an optimal T of n into P of n product of big O of n for computing the sum of n integers. Brent's theorem. Brent's theorem is also a technique for reducing the number of processes needed to solve a particular problem. If an algorithm is designed so that a large number of processes are idle during much of the computation, then Brent's theorem may be of use. This theorem is summarized as follows. Theorem. Any synchronous parallel algorithm that runs in t time steps and consists of a total of n operations can be simulated by p processes in time, that is big O of floor of n by p plus t. Proof. Let n be the number of operations performed at step I in the parallel algorithm. The p processes can simulate step I of the algorithm in big O of ceiling of ni by p time. Thus, the total running time is big O of floor of n by p plus t, since as follows. There are two qualifications we must make to Brent's theorem before we can apply it in the PRAM model. First, we must be able to compute ni at the beginning of step I in big O of ceiling of ni by p time using p processes. That is, we must know how many operations are actually to be performed in step I. And second, we must know exactly how to assign each processor to its job. That is, we must be able to direct each processor to the big O of ceiling of ni by p operations it is to perform in simulating step I. As an example of the application of Brent's theorem, consider the summation problem again. Although the algorithm ran in big O of log n time and used big O of n processes, it only performed big O of n total operations. Thus, by applying Brent's theorem, we have an alternate method for solving this problem in big O of log n time, using big O of n by log n processes. The qualification to Brent's theorem are easily solved in this case, since the number of operations performed in step I is exactly half the number performed in step I minus 1. More specifically, we will take ceiling of log n time simulating the first step when all n processes are active, ceiling of log n by 2 time simulating the second step, ceiling of log n by 4 time for the third, and so on. This clearly sums to big O of log n, giving us an alternative method for summing n integers in big O of log n time using big O of n by log n processes. Basics of randomized algorithms. Randomized algorithms. At least once during the algorithm, a random number is used to make a decision. The running time of the algorithm depends not only on the particular input but also on the random numbers that occur. The worst case running time of a randomized algorithm is often the same as the worst case running time of the non-randomized algorithm. The important difference is that a good randomized algorithm has no bad inputs but only bad random numbers relative to the particular input. Consider two variants of quicksort. Variant A uses the first element as pivot, while variant B uses a randomly chosen element as pivot. In both cases, the worst case running time is big theta of n square because it is possible at each step that the largest element is chosen as pivot. The difference between these worst cases is that there is a particular input can always be presented to variant A to cause the bad running time. Variant A will run in big theta of n square time every single time it is given an already sorted list. If variant B is presented with the same input twice, it will have two different running times depending on what random numbers occur. By using a randomized algorithm, the particular input is no longer important. The random numbers are important and we can get an expected running time, where we now average overall possible random numbers instead of overall possible inputs. Using quicksort with a random pivot gives an big O of n log n expected time algorithm. This means that for any input, including already sorted input, the running time is expected to be big O of n log n based on the statistics of random numbers. An expected running time bound is somewhat stronger than an average case bound, but of course is weaker than the corresponding worst case bound. Random number generators. Since our algorithms require random numbers, we must have a method to generate them. Actually, true randomness is virtually impossible to do on a computer, since these numbers will depend on the algorithm and thus cannot possibly be random. Generally, it suffices to produce pseudo-random numbers, which are numbers that appear to be random. Random numbers have many known statistical properties. Pseudo-random numbers satisfy most of these properties. Suppose we only need to flip a coin, thus we must generate a 0 for heads or 1 for tails randomly. One way to do this is to examine the system clock. The clock might record time as an integer that counts the number of seconds since some starting time. We would then use the lowest bit. The problem is that this does not work well if a sequence of random numbers is needed. 1 second is a long time and the clock might not change at all while the program is running. Even if the time was recorded in units of microseconds, if the program was running by itself, the sequence of numbers that would be generated would be far from random, since the time between calls to the generator would be essentially identical on every program invocation. Then, that what is really needed is a sequence of random numbers. These numbers should appear independent. If a coin is flipped and heads appears, the next coin flip should still be equally likely to come up heads or tails. The simplest method to generate random numbers is the linear congruential generator. Numbers x1, x2, etc. are generated satisfying xi plus 1 equals axi mod m. To start the sequence, some value of x0 must be given. This value is known as the seed. If x0 equals 0, then the sequence is far from random, But if A and M are correctly chosen, then any other 1 less than or equals x naught less than m is equally valid. If m is prime, then xi is never 0. As an example, if m equals 11, a equals 7, and x naught equals 1, then the numbers generated are as follows. Notice that after m minus 1 equals 10 numbers, the sequence repeats. Thus, this sequence has a period of m minus 1, which is as large as possible, by the pigeonhole principle. If m is a prime, there are always choices of A that give a full period of m minus 1. Some choices of A do not. If A equals 5 and x naught equals 1, the sequence has a short period of 5 as follows. If m is chosen to be a large 31-bit prime, the period should be significantly large for most applications. Lehmer suggested the use of the 31-bit prime m equals 231 minus 1 equals 2 147 483 647. For this prime, a equals 48 271 is one of the many values that gives a full period generator. Its use has been well studied and is recommended by experts in the field. This seems like a simple routine to implement. Generally, a class variable is used to hold the current value in the sequence of x's. When debugging a program that uses random numbers, it is probably best to set x naught equals 1 so that the same random sequence occurs all the time. When the program seems to work, either the system clock can be used or the user can be asked to input a value for the seed. It is also common to return a random real number in the open interval 0, 1. 0 and 1 are not possible values. This can be done by dividing by m. From this, a random numbers in any closed interval alpha, beta can be computed by normalizing. This yields the obvious class in below figure, which unfortunately is erroneous. The problem with this class is that the multiplication would overflow. Although this is not an error, it affects the result and thus the pseudo-randomness. Even though we would use 64-bit long, this would slow down the computation. Schrag gave a procedure in which all the calculations can be done on a 32-bit machine without overflow. We compute the quotient and remainder and then define these as Q and R respectively. In our case, Q equals 44,488, R equals 3,339 and R less than Q. If R less than Q, all the remaining terms can be calculated without overflow. This is one of the reasons for choosing A equals 48,271. Furthermore, delta of x, I equals 1 only if the remaining terms evaluate to less than 0. Thus, delta of xi does not need to be explicitly computed but can be determined by a simple test. One might be tempted to assume that all machines have a random number generator as good as the one shown in below figure in their standard library. The lower k-bit cycle with period 2 power k at best. Many other random number generators have much smaller cycles than the one provided in the previous figure. These are not suitable for the case where long sequences of random numbers are needed. C++11 provides a very general framework for the generation of random numbers. In this framework, the generation of random numbers, that is, the type of random number generator used, is separated from the actual distribution used. That is, whether the numbers are uniformly distributed over integers, a range of reals, or follow other distributions, such as the normal distribution or Poisson distribution. The generators that are provided include linear congruential generators with the class template linear congruential engine, which allows the specification of the parameters a, c, and m. Template, type name, unsigned type A, unsigned type C, unsigned type M. Class, linear congruential engine. Along with this type def that yields the random number generator, the minimal standard described earlier. Type def linear congruential engine, unsigned int 48,271, 0, 2 147 483 647, min standard random 0. The following figure illustrates how a random number generator engine can be combined with a distribution, which is a function object, to provide an easy-to-use class for the generation of random numbers. Skip lists. Our first use of randomization is a data structure that supports both searching and insertion in big O of log n expected time, where the expectation is based on the random number generator. It is possible to add deletion and all the operations that involve ordering and obtain expected time bounds that match the average time bounds of binary search trees. The simplest possible data structure to support searching is the linked list. The following figure shows a simple linked list. The time to perform a search is proportional to the number of nodes that have to be examined, which is at most n. The following figure shows a linked list in which every other node has an additional link to the node 2 ahead of it in the list. Because of this, at most, ceiling of n by 2 plus 1 nodes are examined in the worst case. This figure illustrates linked list with links to 2 cells ahead. We can extend this idea and obtain as shown in the following figure. Here, every fourth node has a link to the node 4 ahead. Only ceiling of n by 4 plus 2 nodes are examined. This figure illustrates linked list with links to 4 cells ahead. The limiting case of this argument is shown in the following figure. Every 2 power ith node has a link to the node 2 power I ahead of it. The total number of links has only doubled. But now, at most, ceiling of log n nodes are examined during a search. It is not hard to see that the total time spent for a search is big O of log n, because the search consists of either advancing to a new node or dropping to a lower link in the same node. Each of these steps consumes at most big O of log n total time during a search. Notice that the search in this data structure is essentially a binary search. The problem with this data structure is that it is much too rigid to allow efficient insertion. The key to making this data structure usable is to relax the structure conditions slightly. We define a level k node to be a node that has k links. As shown in the previous figure, the ith link in any level k node, k greater than or equals I, links to the next node with at least I levels. This is an easy property to maintain. However, the previous figure shows a more restrictive property than this. We thus drop the restriction that the ith link links to the node 2 power I ahead, and we replace it with the less restrictive condition above. When it comes time to insert a new element, we allocate a new node for it. We must at this point decide what level the node should be. Examining the previous figure, we find that roughly half the nodes are level 1 nodes, roughly a quarter are level 2, and in general, approximately 1 by 2 power I nodes are level I. We choose the level of the node randomly in accordance with this probability distribution. The easiest way to do this is to flip a coin until a head occurs, and use the total number of flips as the node level. The following figure shows a typical skip list. Given this, the skip list algorithms are simple to describe. To perform a search, we start at the highest link at the header. We traverse along this level until we find that the next node is larger than the one we are looking for, or null pointer. When this occurs, we go to the next lower level and continue the strategy. When progress is stopped at level 1, either we are in front of the node we are looking for or it is not in the list. To perform an insert, we proceed as in a search and keep track of each point where we switch to a lower level. The new node, whose level is determined randomly, is then spliced into the list. This operation is shown in the following figure. A cursory analysis shows that since the expected number of nodes at each level is unchanged from the original, non-randomized algorithm. The total amount of work that is expected to be performed traversing two nodes on the same level is unchanged. This tells us that these operations have big O of log n expected cost. Of course, a more formal proof is required, but it is not much different from this. Skip lists are similar to hash tables in that they require an estimate of the number of elements that will be in the list so that the number of levels can be determined. If an estimate is not available, we can assume a large number or use a technique similar to rehashing. Experiments have shown that skip lists are as efficient as many balanced search tree implementations and are certainly much simpler to implement in many languages. Skip lists also have efficient concurrent implementations, unlike balanced binary search trees. Hence, they are provided in the Java library, though not yet in C++. Bin packing problem. Consider some algorithms to solve the bin packing problem. These algorithms will run quickly but will not necessarily produce optimal solutions. We will prove, however, that the solutions that are produced are not too far from optimal. We are given n items of sizes S1, it goes up to Sn. All sizes satisfy 0, less than Si, less than or equals 1. The problem is to pack these items in the fewest number of bins, given that each bin has unit capacity. As an example, the following figure shows an optimal packing for an item list with sizes 0.2, 0.5, 0.4, 0.7, 0.1, 0.3 and 0.8. Two versions of the bin packing problem. First version, online bin packing problem. Each item must be placed in a bin before the next item can be processed. Second version, offline bin packing problem. In an offline algorithm, we do not need to do anything until all the input has been read. This figure shows optimal packing for the given sequence. Online algorithms. The first issue to consider is whether or not an online algorithm can actually always give an optimal answer, even if it is allowed unlimited computation. Remember that even though unlimited computation is allowed, an online algorithm must place an item before processing the next item and cannot change its decision. To show that an online algorithm cannot always give an optimal solution, we will give it particularly difficult data to work on. Consider an input sequence I1 of m small items of weight 1 by 2 minus epsilon followed by m large items of weight 1 by 2 plus epsilon. Epsilon lies between 0 and 0.01. It is clear that these items can be packed in m bins if we place one small item and one large item in each bin. Suppose there were an optimal online algorithm A that would perform this packing. Consider the operation of algorithm A on the sequence I2 consisting of only m small items of weight 1 by 2 minus epsilon. I2 can be packed in ceiling of m by 2 bins. However, A will place each item in a separate bin. Since A must yield the same results on I2 as it does for the first half of I1, and the first half of I1 is exactly the same input as I2. This means that A will use twice as many bins as is optimal for I2. What we have proved is that there is no optimal algorithm for online bin packing. What the argument above shows is that an online algorithm never knows when the input might end. So, any performance guarantees it provides must hold at every instant throughout the algorithm. There are 3 simple algorithms that guarantee that the number of bins used is no more than twice optimal. Next fit. Probably the simplest algorithm is next fit. When processing any item, we check to see whether it fits in the same bin as the last item. If it does, it is placed there. Otherwise, a new bin is created. This algorithm is incredibly simple to implement and runs in linear time. The following figure shows the packing produced for the same input as the above figure. Not only is next fit simple to program, its worst case behavior is also easy to analyze. First fit. Although next fit has a reasonable performance guarantee, it performs poorly in practice because it creates new bins when it does not need to. In the sample run, it would have placed the item of size 0.3 in either B1 or B2 rather than create a new bin. The first fit strategy is to scan the bins in order and place the new item in the first bin that is large enough to hold it. Thus, a new bin is created only when the results of previous placements have left no other alternative. The following figure shows the packing that results from first fit on our standard input. This figure shows first fit for given sequence. A simple method of implementing first fit would process each item by scanning down the list of bins sequentially. This would take big O of n square. It is possible to implement first fit to run in big O of n log n. At most, one bin can be more than half empty, since if a second bin were also half empty, its contents would fit into the first bin. Thus, we can immediately conclude that first fit guarantees a solution with at most twice the optimal number of bins. On the other hand, the bad case that we used in the proof of next fit's performance bound does not apply for first fit. Thus, one might wonder if a better bound can be proven. The answer is yes, but the proof is complicated. Best fit. The third online strategy is best fit. Instead of placing a new item in the first spot that is found, it is placed in the tightest spot among all bins. A typical packing is shown in the following figure. Notice that the item of size 0.3 is placed in B3 where it fits perfectly instead of B2. One might expect that since we are now making a more educated choice of bins, the performance guarantee would improve. Best fit is never more than roughly 1.7 times as bad as optimal, and the inputs for which it nearly achieves this bound. Nevertheless, best fit is also simple to code, especially if an big O of n log n algorithm is required, and it does perform better for random inputs. Offline algorithms. If we are allowed to view the entire item list before producing an answer, then we should expect to do better. Indeed, since we can eventually find the optimal packing by exhaustive search, we already have a theoretical improvement over the online case. The major problem with all the online algorithms is that it is hard to pack the large items, especially when they occur late in the input. The natural way around this is to sort the items, placing the largest items first. We can then apply first fit or best fit, yielding the algorithms first fit decreasing and best fit decreasing respectively. The following figure shows that in our case this yields an optimal solution, although of course this is not true in general. In this section, we will deal with first fit decreasing. The results for best fit decreasing are almost identical. Since it is possible that the item sizes are not distinct, some authors prefer to call the algorithm first fit non-increasing. We will stay with the original name. We will also assume, without loss of generality, that input sizes are already sorted. The first remark we can make is that the bad case, which showed first fit using 10m bins instead of 6m bins, does not apply when the items are sorted. We will show that if an optimal packing uses m bins, then first fit decreasing never uses more than 4m plus 1 by 3 bins. The result depends on two observations. First, all the items with weight larger than 1 by 3 will be placed in the first m bins. This implies that all the items in the extra bins have weight at most 1 by 3. The second observation is that the number of items in the extra bins can be at most m minus 1. Combining these two results, we find that at most ceiling of m minus 1 by 3 extra bins can be required. We now prove these two observations. In practice, first fit decreasing performs extremely well. If sizes are chosen uniformly over the unit interval, then the expected number of extra bins is big theta of square root of m. Bin packing is a fine example of how simple greedy heuristics can give good results. Flynn's classification. This classification was first studied and proposed by Michael Flynn. Flynn did not consider the machine architecture for classification of parallel computers. He introduced the concept of instruction and data streams for categorizing of computers. All the computers classified by Flynn are not parallel computers, but to grasp the concept of parallel computers, it is necessary to understand all types of Flynn's classification. Since this classification is based on instruction and data streams, first we need to understand how the instruction cycle works. Instruction cycle. The instruction cycle consists of a sequence of steps needed for the execution of an instruction in a program. A typical instruction in a program is composed of two parts, opcode and operand. The operand part specifies the data on which the specified operation is to be done, as shown in this figure. The operand part is divided into two parts, addressing mode and the operand. Addressing mode. It specifies the method of determining the addresses of the actual data on which the operation is to be performed. Operand part is used as an argument by the method in determining the actual address. The control unit of the CPU of the computer fetches instructions in the program, one at a time. The fetched instruction is then decoded by the decoder, which is a part of the control unit, and the processor executes the decoded instructions. The result of execution is temporarily stored in Memory Buffer Register, MBR, also called Memory Data Register. The normal execution steps are shown in this figure. Instruction stream and data stream. The term stream refers to a sequence of flow of either instructions or data operated on by the computer. In the complete cycle of instruction execution, a flow of instructions from main memory to the CPU is established. This flow of instruction is called instruction stream. Similarly, there is a flow of operands between processor and memory bidirectionally. This flow of operands is called data stream. These two types of streams are shown in this figure. Thus, it can be said that the sequence of instructions executed by CPU forms the instruction streams, and a sequence of data, operands, required for execution of instructions form the data streams. Flynn's classification. Flynn's classification is based on multiplicity of instruction streams and data streams observed by the CPU during program execution. Let IS and DS are minimum number of streams flowing at any point in the execution. Then the computer organization can be categorized as follows. Single instruction and single data stream, SISD. In this organization, sequential execution of instructions is performed by one CPU containing a single processing element, PE, that is ALU, under one control unit as shown in this figure. Therefore, SISD machines are conventional serial computers that process only one stream of instructions and one stream of data. This type of computer organization is denoted as IS equals DS, which is equals 1. Examples of SISD machines include CDC 6600, which is unpipelined but has multiple functional units. CDC 7600, which has a pipelined arithmetic unit. Single instruction and multiple data stream, SIMD. In this organization, multiple processing elements work under the control of a single control unit. It has one instruction and multiple data stream. All the processing elements of this organization receive the same instruction broadcast from the CU. Main memory can also be divided into modules for generating multiple data streams, acting as a distributed memory as shown in this figure. Therefore, all the processing elements simultaneously execute the same instruction and are said to be lockstepped together. Each processor takes the data from its own memory and hence it has distinct data streams. Some systems also provide a shared global memory for communications. Every processor must be allowed to complete its instruction before the next instruction is taken for execution. Thus, the execution of instructions is synchronous. Examples of SIMD organization are ILLIAC, 4, PEPE, BSP, STARAN, MPP, DAP, and the connection machine CM1. This type of computer organization is denoted as IS equals 1 and DS greater than 1. Multiple instruction and single data stream MISD. In this organization, multiple processing elements are organized under the control of multiple control units. Each control unit is handling one instruction stream and processed through its corresponding processing element. But each processing element is processing only a single data stream at a time. Therefore, for handling multiple instruction streams and single data stream, multiple control units and multiple processing elements are organized in this classification. All processing elements are interacting with the common shared memory for the organization of single data stream as shown in this figure. This type of computer organization is denoted as IS greater than 1 and DS equals 1. This classification is not popular in commercial machines as the concept of single data streams executing on multiple processors is rarely applied. But for the specialized applications, MISD organization can be very helpful. For example, real-time computers need to be fault-tolerant where several processors execute the same data for producing the redundant data. This is also known as N-version programming. All these redundant data are compared as results which should be same. Otherwise, faulty unit is replaced. Thus, MISD machines can be applied to fault-tolerant real-time computers. Multiple instruction and multiple data stream MIMD. In this organization, multiple processing elements and multiple control units are organized as in MISD. But the difference is that now in this organization, multiple instruction streams operate on multiple data streams. Therefore, for handling multiple instruction streams, multiple control units and multiple processing elements are organized such that multiple processing elements are handling multiple data streams from the main memory are shown here. The processors work on their own data with their own instructions. Tasks executed by different processors can start or finish at different times. They are not lockstep as in SIMD computers but run asynchronously. This classification actually recognizes the parallel computer. That means in the real sense, MIMD organization is said to be a parallel computer. All multiprocessor systems fall under this classification. Examples include D825, Cray2, S1, Cray XMP, HEP, IBM 370-168MP, UNIVAC 1100, 80, IBM 3081, 3084, C.M Star, BBN, Butterfly, IPSC. This type of computer organization is denoted as IS greater than 1 and DS greater than 1. Parallel computers execute the instructions in MIMD mode. GCD algorithm. Greatest Common Divisor, GCD. Euclid's algorithm for efficiently computing the greatest common divisor of two integers. When we analyze the running time, we shall see a surprising connection with the Fibonacci numbers which yield a worst-case input for Euclid's algorithm. We restrict ourselves in this section to non-negative integers. This restriction is justified by the following equation which states that GCD of A, B equals GCD of modulus of A, modulus of B. We can compute GCD of A, B for positive integers A and B from the prime factorizations of A and B. Indeed, if A equals P1 power E1 up to PR power ER, B equals P1 power F1 up to PR power FR, with zero exponents being used to make the set of primes P1 up to Pr the same for both A and B. Then, the best algorithms to date for factoring do not run in polynomial time. Thus, this approach to computing greatest common divisors seems unlikely to yield an efficient algorithm. Euclid's algorithm for computing greatest common divisors relies on the following theorem. Theorem: GCD recursion theorem. For any non-negative integer a and any positive integer b, GCD of a, b equals GCD of b, a mod b. Euclid's algorithm. The Elements of Euclid describes the following GCD algorithm, although it may be of even earlier origin. Express Euclid's algorithm as a recursive program based directly on the GCD recursion theorem. The inputs a and b are arbitrary non-negative integers. This figure shows Euclid's algorithm. As an example of the running of Euclid, consider the computation of GCD 30,21. Euclid 30,21 equals Euclid 21,9. It produced result 3. This computation calls Euclid recursively 3 times. The correctness of Euclid follows from GCD recursion theorem and the property that if the algorithm returns a in line 2, then b equals 0, so that GCD of a, b equals GCD of a, 0 equals a. The algorithm cannot recurse indefinitely since the second argument strictly decreases in each recursive call and is always non-negative. Therefore, Euclid always terminates with the correct answer. The running time of Euclid's algorithm. We analyze the worst-case running time of Euclid as a function of the size of a and b. We assume with no loss of generality that a greater than b, which is greater than or equals 0. To justify this assumption, observe that if b greater than a, which is greater than or equals 0, then Euclid of a, b immediately makes the recursive call Euclid of b, a. That is, if the first argument is less than the second argument, Euclid spends one recursive call swapping its arguments and then proceeds. Similarly, if b equals a greater than 0, the procedure terminates after one recursive call since a mod b equals 0. The overall running time of Euclid is proportional to the number of recursive calls it makes. Our analysis makes use of the Fibonacci numbers fk defined by the recurrence, which is shown in next figure. The extended form of Euclid's algorithm. Now rewrite Euclid's algorithm to compute additional useful information. Specifically, we extend the algorithm to compute the integer coefficients x and y such that d equals GCD of a, b, which is equals ax plus by. Note that x and y may be 0 or negative. We shall find these coefficients useful later for computing modular multiplicative inverses. The procedure extended Euclid takes as input a pair of non-negative integers and returns a triple of the form d, x, y that satisfies the above equation. The extended Euclid procedure is a variation of the Euclid procedure. Line 1 is equivalent to the test b equals 0 in line 1 of Euclid. If b equals 0, then extended Euclid returns not only d equals a in line 2, but also the coefficients x equals 1 and y equals 0, so that a equals ax plus by. If b not equals 0, extended Euclid first computes d dash, x dash, y dash, such that d dash equals GCD of b, a mod b and d dash equals dx dash plus a mod b into y dash. As for Euclid, we have in this case d equals GCD of a, b, which is equals d dash equals GCD of b, a mod b. To obtain x and y such that d equals ax plus by, start by rewriting the above equation using the equation d equals d dash, and we get as shown in below. Thus, choosing x equals y dash and y equals x double dash minus floor of a by b y dash satisfies the equation d equals ax plus by, proving the correctness of extended Euclid. Since the number of recursive calls made in Euclid is equal to the number of recursive calls made in extended Euclid. The running times of Euclid and extended Euclid are the same, 2 within a constant factor. That is, for a greater than b, which is greater than 0, the number of recursive calls is big O of log b. List ranking. Recursive doubling. Recursive doubling is a technique that can be thought of as being a complement of the divide and conquer paradigm, whereas divide and conquer is a top-down technique. Recursive doubling is a bottom-up technique. The main idea is that we start with small subsets and iteratively combine them in pairs until we have solved the whole problem. We describe the recursive doubling technique with an example, list ranking. List ranking. In the list ranking problem, we are given a linked list represented as an array of pointers resident in memory and are asked to compute the distance from the tail of each element in the list. We discuss here the classic parallel algorithm for this problem. The main idea is to assign a processor to each element in the list and at each time step set each element's pointer to the pointer of its successor. With each iteration, the distance that each element has looked ahead is doubled. Hence, in at most big O of log n iterations, each element will be pointing at the tail. More specifically, let P of V denote the pointer from V and let tail denote the node which is the tail of the list. Also store a label R of V with each node V, which is initially 1 for all nodes except the tail, whose R label is 0. This label will eventually store the rank of V in the list. In each time step, one performs the following operation for each node V in parallel, which is shown in the following figures. Parallel prefix. There is a related problem, the parallel prefix problem, which can also be solved by recursive doubling as shown in the following figure. We are given a list A, which has the elements a1 up to an of integers, and compute all the prefix sums sk equals summation I equals 1 to k ai. Using the recursive doubling technique, we can easily do this in big O of log n time using big O of n processes. Unlike the list ranking problem, we can easily make a fairly straightforward application of the sequential subsets technique to the parallel prefix problem as shown in below figure. In this case, we can reduce the number of processes to big O of n by log n and still achieve an big O of log n running time gives us an optimal T of n into P of n product. The method for doing this is the following. Divide the array A into n by log n subarrays of size log n each and compute the sum of each subarray sequentially using a single processor. Then proceed with the prefix computation just as before, using these partial sums as the elements. After completing the prefix computation on these elements, we simply backtrack through each of the n by log n subarrays, one processor per subarray, to compute all the partial sums. The parallel prefix problem arises as a subproblem in a number of other list manipulation problems. We illustrate this with two examples. Example 1. Consider the following array compression problem. Given an n-element array A, in which each element is flagged as being either marked or unmarked, construct an array B, listing the marked elements of A in order as they appear in A, that is, B is the marked subsequence of A. The method is to associate a value of 1 with each marked element and a value of 0 with each unmarked element. By performing a parallel prefix computation, we can determine the rank in the compressed list B for each marked element in A. It is then an easy operation to write each marked element in A to its appropriate position in B. This can clearly be done in big O of log n time using big O of n processes. Example 2. Consider the array splitting problem. Given an array A consisting of n integers, decompose A into subarrays A1 up to Am such that each AI consists of repetitions of the same integer, which differs from the integer repeated in AI-1 and the one repeated in AI plus 1. That is, k belongs to AI implies k does not belongs to AI minus 1 and k does not belongs to AI plus 1. This can be done by associating a value of 1 with each element in A and performing the combining step of the parallel prefix algorithm for each element as long as all the preceding elements are identical. This will give us the rank of each element A in its subarray. Then perform another parallel prefix operation to determine which subarray A belongs to, that is, determining the value of I. Polynomial time approximate schemes. There are some problems for which we can construct delta approximation algorithms that run in polynomial time with delta equals 1 plus epsilon for any fixed value epsilon greater than 0. The running time of such a collection of algorithms depends both on n, the size of the input, and also on the fixed value epsilon. We refer to such a collection of algorithms as a polynomial time approximation scheme or PTAS. When we have a polynomial time approximation scheme for a given optimization problem, we can tune our performance guarantee based on how much time we can afford to spend. Ideally, the running time is polynomial in both n and 1 by epsilon, in which case we have a fully polynomial time approximation scheme. Polynomial time approximation schemes take advantage of a property that some hard problems possess, that they are rescalable. A problem is said to be rescalable if an instance x of the problem can be transformed into an equivalent instance x dash, that is, one with the same optimal solution by scaling the cost function c. For example, TSP is rescalable. Given an instance g of TSP, we can construct an equivalent instance g dash by multiplying the distance between every pair of vertices by a scaling factor s. The traveling salesperson 2 in g dash will be the same as in g, although its cost will now be multiplied by s. Fully polynomial time approximation scheme for knapsack. To be more concrete, let us give a fully polynomial time approximation scheme for the optimization version of a well-known problem, knapsack. In the optimization version of this problem, we are given a set S of items numbered 1 to n, together with a size constraint S. Each item I in S is given an integer size Si and worth Wi, and we are asked to find a subset T of S such that T maximizes the worth. W equals summation of I belongs to T, Wi, while satisfying summation of I belongs to T, Si less than or equals S. We desire a PTAS that produces A of 1 plus epsilon approximation for any given fixed constant epsilon. That is, such an algorithm should find a subset T dash satisfying the size constraint such that if we define W dash equals summation I belongs to T dash Wi, then opt less than or equals 1 plus epsilon into W dash, where opt is the optimal worth summation taken over all possible subsets satisfying the total size constraint. To prove that this inequality holds, we will actually prove that W dash greater than or equals 1 minus epsilon by 2 into opt. For epsilon, which lies between 0 and 1, this will be sufficient. However, since for any fixed epsilon which lies between 0 and 1, 1 by 1 minus epsilon by 2 less than 1 plus epsilon. To derive a PTAS for knapsack, we take advantage of the fact that this problem is rescalable. Suppose we are given a value of epsilon with epsilon lies between 0 and 1. Let W max denote the maximum worth of any item in S. Without loss of generality, we assume that the size of each item is at most S. For an item larger than this would not fit in the knapsack. Thus, the item with worth W max defines a lower bound for the optimal value, that is, W max less than or equals opt. Likewise, we can define an upper bound on the optimal solution by noting that the knapsack can at most contain all n items in S, each of which has worth at most W max, thus opt less than or equals n W max. To take advantage of the rescalability of knapsack, we round each worth value wi to wi dash. The nearest smaller multiple of m equals epsilon w max by 2n. Let us denote the rounded version of s as s dash, and let us also use opt dash to denote the solution for this rounded version s dash. Note that by simple substitution, opt less than or equals 2n square m by epsilon. Moreover, opt dash less than or equals opt, since we rounded every worth value in s down to form s dash. Thus, opt dash less than or equals 2n square m by epsilon. Therefore, let us turn to our solution for the rounded version s dash of the knapsack problem for s. Since every worth value in s dash is a multiple of m, any achievable worth of a collection of items taken from s dash is also a multiple of m. Moreover, there are just n equals ceiling of 2n square by epsilon, such multiples that need to be considered because of the upper bound on opt dash. We can use dynamic programming to construct an efficient algorithm for finding the optimal worth for s dash. In particular, let us define the parameter s of I, j equals the size of the smallest set of items in 1, 2, it goes up to j with worth im. The key insight to the design of a dynamic programming algorithm for solving the rounded knapsack problem is the observation that we can write s of I, j equals min of s of I, j minus 1 sj plus s of I minus wj dash by m, j minus 1 for I equals 1 to n and j equals 1 to n. The above equation for s of I, j follows from the fact that item j will either contribute or not contribute to the smallest way of achieving worth im from the items in 1 up to j. In addition, note that for the best case, j equals 0 when no items at all are included in the knapsack. Then s of I, 0 equals positive infinity for I equals 1 to n. That is, such a size is undefined. In addition, s of 0, j equals 0 for j equals 1 up to n. Since we can always achieve worth 0 by including no items in the knapsack, the optimal value is defined by opt dash equals max of im such that s of I, n less than or equals s. This is the value that is output by our PTAS algorithm. Analysis of the PTAS for knapsack. We can easily convert the above description into a dynamic programming algorithm that computes opt dash in big O of n cube by epsilon time. Such an algorithm gives us the value of an optimal solution, but we can easily translate the dynamic programming algorithm for computing the size into 1 for the actual set of items. Let us consider then how good an approximation opt dash is for opt. Wi of each item I by at most m equals epsilon w max by 2n. Thus, opt dash greater than or equals opt minus epsilon w max by 2. Since the optimal solution can contain at most n items, since opt greater than or equals w max, this in turn implies that opt dash greater than or equals opt minus epsilon opt by 2 equals 1 minus epsilon by 2 into opt. Thus, opt less than or equals 1 plus epsilon opt dash. The running time of our approximation algorithm is big O of n cube by epsilon. Our scheme of designing an efficient algorithm for any given epsilon greater than 0 gives rise to a fully polynomial approximation scheme, since the running time is polynomial in both n and 1 by epsilon. Scheduling problems. Given jobs j1 up to jn, all with known running times t1 up to tn respectively, we have a single processor. What is the best way to schedule these jobs in order to minimize the average completion time? In this section, we will assume Non-preemptive scheduling. Once a job is started, it must run to completion. As an example, suppose we have the 4 jobs and associated running times as shown in the following figure. One possible schedule is shown in the following figure because J1 finishes in 15 time units, J2 in 23, J3 in 26 and J4 in 36. The average completion time is 25. A better schedule which yields a mean completion time of 17.75 is shown in the following figure. In this, the schedule is arranged by shortest job first. We can show that this will always yield an optimal schedule. Let the jobs in the schedule be Ji1, Ji2, it goes up to Jin. The first job finishes in time Ti1. The second job finishes after Ti1 plus Ti2. And the third job finishes after Ti1 plus Ti2 plus Ti3. From this, the total cost C of the schedule are shown in below. From the above equation, the first sum is independent of the job ordering, so only the second sum affects the total cost. Suppose that in an ordering, there exists some x greater than y such that Tix less than Tiy. Then a calculation shows that by swapping Jix and Jiy, the second sum increases, decreasing the total cost. Thus, any schedule of jobs in which the times are not monotonically non-decreasing must be suboptimal. The only schedules left are those in which the jobs are arranged by smallest running time first, breaking ties arbitrarily. This result indicates the reason the operating system scheduler generally gives precedence to shorter jobs. Multiprocessor case. Extend this problem to the case of several processors. Again, we have jobs J1 up to Jn with associated running times T1 up to Tn and a number P of processes. We will assume, without loss of generality, that the jobs are ordered shortest running time first. As an example, suppose P equals 3 and the jobs are shown in the following figure. The below figure shows an optimal arrangement to minimize mean completion time. Jobs J1, J4 and J7 are run on Processor 1. Processor 2 handles J2, J5 and J8 and Processor 3 runs the remaining jobs. The total time to completion is 165 for an average of 165 by 9 equals 18.33. The algorithm to solve the multiprocessor case is to start jobs in order, cycling through processes. It is not hard to show that no other ordering can do better, although if the number of processes P evenly divides the number of jobs N, there are many optimal orderings. This is obtained by, for each 0 less than or equals I which is less than N by P, placing each of the jobs JIP plus 1 through JI plus 1 into P on a different processor. The following figure shows a second optimal solution. Even if P does not divide N exactly, there can still be many optimal solutions, even if all the job times are distinct. Minimizing the final completion time. Suppose we are only concerned with when the last job finishes. In our 2 examples above, these completion times are 40 and 38 respectively. The following figure shows that the minimum final completion time is 34. And this clearly cannot be improved because every processor is always busy. Although this schedule does not have minimum mean completion time, it has merit in that the completion time of the entire sequence is earlier. If the same user owns all these jobs, then this is the preferable method of scheduling. Although these problems are very similar, this new problem turns out to be NP-complete. It is just another way of phrasing the knapsack or bin packing problems. Thus, minimizing the final completion time is apparently much harder than minimizing the mean completion time. Set cover problem. The set covering problem is an optimization problem that models many problems that require resources to be allocated. Its corresponding decision problem generalizes the NP-complete vertex cover problem and is therefore also NP-hard. The approximation algorithm developed to handle the vertex cover problem doesn't apply here. However, and so we need to try other approaches. We shall examine a simple greedy heuristic with a logarithmic approximation ratio. That is, as the size of the instance gets larger, the size of the approximate solution may grow relative to the size of an optimal solution. Because the logarithm function grows rather slowly, however, this approximation algorithm may nonetheless give useful results. An instance x, f of the set covering problem consists of a finite set x and a family f of subsets of x, such that every element of x belongs to at least one subset in f, as shown in below. We say that a subset S belongs to f covers its elements. The problem is to find a minimum size subset. C is a subset of f whose numbers cover all of x, as shown here. The following figure illustrates an instance x, f of the set covering problem, where x consists of the 12 black points and f contains the following elements. A minimum size set cover is C, which has the elements S3, S4 and S5 with size 3. The greedy algorithm produces a cover of size 4 by selecting either the sets S1, S4, S5 and S3 or the sets S1, S4, S5 and S6 in order. The size of C is the number of sets it contains rather than the number of individual elements in these sets. Since every subset C that covers X must contain all modulus of X individual elements. In the above figure, the minimum set cover has size 3. The set covering problem abstracts many commonly arising combinatorial problems. As a simple example, suppose that X represents a set of skills that are needed to solve a problem and that we have a given set of people available to work on the problem. We wish to form a committee containing as few people as possible, such that for every requisite skill in X, at least one member of the committee has that skill. In the decision version of the set covering problem, we ask whether a covering exists with size at most k, where k is an additional parameter specified in the problem instance. In the above figure, greedy set cover adds to C in order the sets S1, S4 and S5 followed by either S3 or S6. Greedy approximation algorithm. The greedy method works by picking at each stage the set S that covers the greatest number of remaining elements that are uncovered. Greedy approximation algorithm is shown in below figure. The algorithm works as follows. The set U contains at each stage the set of remaining uncovered elements. The set C contains the cover being constructed. Line 4 is the greedy decision-making step, choosing a subset S that covers as many uncovered elements as possible. After S is selected, line 5 removes its elements from U and line 6 places S into C. When the algorithm terminates, the set C contains a subfamily of F that covers X. We can easily implement greedy set cover to run in time polynomial in modulus of X and modulus of F. Since the number of iterations of the loop on lines 3 to 6 is bounded from above by min of modulus of X, modulus of F, and we can implement the loop body to run in time big O of modulus of X and modulus of F, a simple implementation runs in time big O of modulus of X, modulus of F, min of modulus of X, modulus of F. Analysis. Now show that the greedy algorithm returns a set cover that is not too much larger than an optimal set cover. For convenience, here we denote the dth harmonic number as shown in below. Hd equals summation of I equals 1 to d 1 by I. As a boundary condition, h of 0 equals 0. SIMD algorithms for simple problems. Single instruction multiple data SIMD is a class of parallel computers in Flint's taxonomy. It describes computers with multiple processing elements that perform the same operation on multiple data points simultaneously. Thus, such machines exploit data-level parallelism but not concurrency. There are simultaneous parallel computations but only a single process instruction at a given moment. SIMD is particularly applicable to common tasks like adjusting the contrast in a digital image or adjusting the volume of digital audio. Most modern CPU designs include SIMD instructions in order to improve the performance of multimedia use. In SIMD process, one operation produces multiple results as shown here. SIMD example, matrix multiplication. In the following, WT denotes the number of scalar values with in a SIMD vector of type T, sometimes also called the number of SIMD lanes. Matrix multiplication introduction. Matrix multiplication takes two two-dimensional arrays as input, sizes n by k and k by m, and produces one two-dimensional array as output, size n by m. Equation. It shows an example 4 by 3 into 3 by 2 gives 4 by 2. The values for matrix C are calculated as Ci, j equals summation k A k B k, j. Matrix memory layout. There are two conventional memory layouts used for storing matrices. Row major. Consecutive elements of the rows of the matrix are contiguous in memory. Consequently, row vectors out of the matrix are contiguous in memory. Column major. Consecutive elements of the columns of the matrix are contiguous in memory. Consequently, column vectors out of the matrix are contiguous in memory. The basic matrix multiplication algorithm is shown in below figure. Matrix multiplication. Given three arrays declared as float A of n by n, float B of n by n, and float C of n by n, the matrix multiplication A into B equals C can be implemented as shown in the above figure. For large matrices, this algorithm is cache inefficient. The cache efficiency can be improved via blocking. The resulting implementation may use up to 12 nested loops instead of the 3 shown in the above figure. For large matrices, cache optimization is ultimately more important than vectorization of the algorithm. Vectorization opportunities. The basic vectorization of the matrix multiplication algorithm shown in the following figure. The algorithm executes n-cube multiplications, all of which are independent and would execute in any order. The algorithm also executes n-1 into n square additions, all of which depend on the result of either a multiplication or another addition. Floating point addition is not commutative. However, for matrix multiplication, we may reorder the additions because it only distributes the statistical error differently. Explicit vectorization partially solves this issue of lost information about data parallelism. Explicit vectorization can either be expressed via loops with vector semantics or types with data parallel operations. One approach for vectorization of matrix multiplication builds upon vectorizing scalar products, row vectors times column vectors. Example, C 0, 0 equals A 0, 0, B 0, 0 plus A 0, 1, B 1, 0 plus A 0, 2, B 2, 0. Since this requires a reduction and leads to a scalar store, this is not the most efficient vectorization. A second approach multiplies a column vector from A with a single scalar entry from B, which is broadcast to a full SIMD vector as shown here. The resulting Ci, j power k values subsequently need to be added up. Ci, j equals summation k ci, j power k. These summations can execute independently for different I, j pairs. Thus, we reuse the vectors to execute the additions in parallel. The resulting vector in C is a column vector. A third approach uses row vectors instead of column vectors, as shown below. Since we will use row major storage for the matrices, this leads to efficient SIMD vector loads and stores, and thus the preferred vectorization approach. Lines 4 to 6 calculate WT entries for the result matrix C in parallel. In line 4, one entry from A is read at ai, 0 and WT entries from B are read in parallel at B0, j. It goes up to B0, j plus WT minus 1. The multiplication between these two objects expresses a component-wise multiplication of two SIMD vectors. Therefore, the ai, 0 value is broadcast to a full SIMD vector with WT entries, all containing the ai, 0 value. The variable Cij thus stores the result of the below vector. In line 6, the results of the following vectors are added component-wise to Cij. The algorithm thus implements the parallel expression of the matrix multiplication. Line 8 finally stores the WT scalar values from the local variable Cij to the two-dimensional array C, starting at the address &Cij and overwriting WT consecutive values of type T. The implementation in listing 2 makes two assumptions about the B and C arrays. The allocated row size of the matrix storage is a multiple of V size method, line 3, and thus larger than n if necessary. The addresses of the first entries &x00 are aligned correctly for aligned loads and stores line 4, 6 and 8. Consequently, a matrix T, n class can be declared as shown in the following figure. Vector width. Thus, a target without SIMD support would use WT equals 1 and an accelerator card, a large value such as WT equals 32 or larger. The description of the matrix multiplication algorithm has an arbitrary width of data parallelism. For large WT, the memory overhead for small matrices may be unreasonably large because of the row padding for alignment. For small matrices, the vector T class might not be the best solution for fully portable and highly efficient code. SIMD array Tn might be better suited for small matrices. Optimizations. Besides caches, for large matrices, the load or store unit is a limiting factor already for small matrices. This can be optimized via unrolling in such a way that fewer loads must be executed. By unrolling the outer loop over I by a factor u, the vector load from Bkj can be reused u times. The following figure shows the complete code for a matrix multiplication. This figure shows that the approach can be directly translated to the SIMD type variant. Note also that the inner loops execute the expression V of &Bkj, Vc aligned with the same k and j. The compiler has enough information available to optimize the multiple load expressions to a single load and reuse the register. The second optimization, which is shown in the above figure, interleaves the final multiply add with the store. The lines 20 and 36 would execute in the preceding loop. By moving them between the stores, the pressure on the store port is relieved. If the code is compiled for a target system supporting FMA instructions, the compiler can fuse the multiplication and addition operators in the middle or back end. This does not require extra effort in the vector T implementation. Example, expression templates would be used to generate FMA calls already in the library. The important point is that vector T provides an intuitive syntax API without loss of flexibility in the compiler, middle and back ends. The matrix multiplication example presented above uses scalar types for data storage and SIMD types for data processing. It would be possible to build the matrix storage with SIMD types and thus eliminate the explicit load and store expressions. The traveling salesman problem. Given a complete undirected graph G equals V, E that has a non-negative integer cost C of U, V associated with each edge, U, V belongs to E, and we must find a Hamiltonian cycle, a tour of G with minimum cost. As an extension of our notation, let C of A denote the total cost of the edges in the subset A is a subset of E, as shown here. In many practical situations, the least costly way to go from a place U to a place W is to go directly, with no intermediate steps. Put another way, cutting out an intermediate stop never increases the cost. We formalize this notion by saying that the cost function C satisfies the triangle inequality if for all vertices U, V, W belongs to capital V. Cost of U, W lesser than or equals C of U, V plus C of V, W. The triangle inequality seems as though it should naturally hold, and it is automatically satisfied in several applications. For example, if the vertices of the graph are points in the plane and the cost of traveling between two vertices is the ordinary Euclidean distance between them, then the triangle inequality is satisfied. Furthermore, many cost functions other than Euclidean distance satisfy the triangle inequality. The traveling salesman problem is NP-complete even if we require that the cost function satisfy the triangle inequality. Thus, we should not expect to find a polynomial time algorithm for solving this problem exactly. Instead, we look for good approximation algorithms. We examine a two approximation algorithm for the traveling salesman problem with the triangle inequality. Show that without the triangle inequality, a polynomial time approximation algorithm with a constant approximation ratio does not exist unless P equals NP. The traveling salesman problem with the triangle inequality. First, compute a structure of a minimum spanning tree whose weight gives a lower bound on the length of an optimal traveling salesman tour. Then, use the minimum spanning tree to create a tour whose cost is no more than twice that of the minimum spanning tree's weight, as long as the cost function satisfies the triangle inequality. The following figure shows the algorithm implements this approach, calling the minimum spanning tree algorithm MST prime as a subroutine. The parameter G is a complete undirected graph, and the cost function C satisfies the triangle inequality. A pre-ordered tree walk recursively visits each vertex in the tree, listing a vertex when it is first encountered before visiting any of its children. The following figures illustrates the operation of approx TSP tour. Part A of the figure shows a complete undirected graph. Vertices lie on intersections of integer grid lines. For example, F is 1 unit to the right and 2 units up from H. The cost function between 2 points is the ordinary Euclidean distance. Part B of the figure shows the minimum spanning tree T grown from root vertex A. It's computed by MST prime algorithm. Vertex A is the root vertex. Only edges in the minimum spanning tree are shown. The vertices happen to be labeled in such a way that they are added to the main tree by MST prime in alphabetical order. Part C of the figure shows a walk of T starting at A. A full walk of the tree visits the vertices in the order as shown. A pre-order walk of T lists a vertex just when it is first encountered, as indicated by the dot next to each vertex, yielding the ordering as follows. Part D of the above figure shows a tour obtained by visiting the vertices in the order given by the pre-order walk, which is the tour H returned by approx TSP2 its total cost is approximately 19.074. Part E of the above figure shows an optimal tour H star for the original complete graph. Its total cost is approximately 14.715. With a simple implementation of MST prime, the running time of approx TSP tour is big theta of V square. Show that if the cost function for an instance of the traveling salesman problem satisfies the triangle inequality, then approx TSP tour returns a tour whose cost is not more than twice the cost of an optimal tour. The general traveling salesman problem. If we drop the assumption that the cost function C satisfies the triangle inequality, then we cannot find good approximate tours in polynomial time unless P equals NP. Theorem. If P not equals NP, then for any constant rho greater than or equals 1, there is no polynomial time approximation algorithm with approximation ratio rho for the general traveling salesman problem. Suppose that given an NP-hard problem X, we can produce in polynomial time a minimization problem Y such that S instances of X correspond to instances of Y with value at most K for some K, but that no instances of X correspond to instances of Y with value greater than K. Then we have shown that unless P equals NP, there is no polynomial time approximation algorithm for problem Y. Vertex cover problem. A vertex cover of an undirected graph G equals V, E is a subset. V dash is a subset of V such that if U, V belongs to E, then U belongs to capital V dash or V belongs to capital V dash or both. That is, each vertex covers its incident edges, and a vertex cover for G is a set of vertices that covers all the edges in E. The size of a vertex cover is the number of vertices in it. For example, the graph in below figure has a vertex cover W, Z of size 2. The vertex cover problem is to find a vertex cover of minimum size in a given graph. Restating this optimization problem as a decision problem, we wish to determine whether a graph has a vertex cover of a given size K. As a language we define vertex cover equals G, K. Graph G has a vertex cover of size K. The following theorem shows that this problem is NP complete. Theorem. The vertex cover problem is NP complete. Proof. We first show that vertex cover belongs to NP. Suppose we are given a graph G equals V, E and an integer K. The certificate we choose is the vertex cover. V dash is a subset of V itself. The verification algorithm affirms that modulus of V dash equals K, and then it checks for each edge U, V belongs to E that U belongs to V dash or V belongs to V dash. We can easily verify the certificate in polynomial time. We prove that the vertex cover problem is NP-hard by showing that clique polynomial reduction vertex cover. This reduction relies on the notion of the complement of a graph. Given an undirected graph G equals V, E, we define the complement of G as G bar equals V, E bar, where E bar equals U, V such that U, V belongs to V, U not equals V, and U, V does not belongs to E. In other words, G bar is the graph containing exactly those edges that are not in G. Below figure shows a graph and its complement and illustrates the reduction from clique to vertex cover. The reduction algorithm takes as input an instance G, K of the clique problem. It computes the complement G, which we can easily do in polynomial time. The output of the reduction algorithm is the instance G bar, modulus of V minus K of the vertex cover problem. To complete the proof, we show that this transformation is indeed a reduction. The graph G has a clique of size K if and only if the graph G bar has a vertex cover of size modulus of V minus K. Suppose that G has a clique V dash is a subset of V with modulus of V dash equals K. We claim that V minus V dash is a vertex cover in G bar. Let U, V be any edge in E bar. Then U, V does not belongs to E, which implies that at least one of U or V does not belongs to V dash, since every pair of vertices in V dash is connected by an edge of E. Equivalently, at least one of U or V is in V minus V dash, which means that edge U, V is covered by V minus V dash. Since U, V was chosen arbitrarily from E bar, every edge of E bar is covered by a vertex in V minus V dash. Hence, the set V minus V dash, which has size modulus of V minus K, forms a vertex cover for G bar. Conversely, suppose that G bar has a vertex cover, V dash is a subset of V, where modulus of V dash modulus of V minus K. Then, for all U, V belongs to V, if U, V belongs to E bar, then U belongs to V dash or V belongs to V dash or both. The contrapositive of this implication is that for all U, V belongs to capital V, if U does not belongs to V dash and V does not belongs to V dash, then U, V belongs to E. In other words, V minus V dash is a clique and it has size modulus of V minus V dash equals K. Since vertex cover is NP complete, we don't expect to find a polynomial time algorithm for finding a minimum size vertex cover. Polynomial time approximation algorithm produces approximate solutions for the vertex cover problem. The size of a vertex cover produced by the algorithm is at most twice the minimum size of a vertex cover. May be able to design a polynomial time approximation algorithm that obtains near optimal solutions even though finding an optimal solution is NP complete. Optimal vertex cover problem. The vertex cover problem is to find a vertex cover of minimum size in a given undirected graph. We call such a vertex cover an optimal vertex cover. This problem is the optimization version of an NP-complete decision problem. Even though we don't know how to find an optimal vertex cover in a graph G in polynomial time, we can efficiently find a vertex cover that is near optimal. The following figure shows an approximation algorithm which takes as input an undirected graph G and returns a vertex cover whose size is guaranteed to be no more than twice the size of an optimal vertex cover. The variable C contains the vertex cover being constructed. Line 1 initializes C to the empty set. Line 2 sets E dash to be a copy of the edge set G and E of the graph. The loop of lines 3 to 6 repeatedly picks an edge U, V from E dash, adds its endpoints U and V to C. The running time of this algorithm is big O of V plus E using adjacency lists to represent E dash. The below figures illustrates how approx vertex cover operates on an example graph. Part A of this figure shows the input graph G, which has 7 vertices and 8 edges. Part B of this figure shows the edge B, C, shown heavy, is the first edge chosen by approx vertex cover. Vertices B and C, shown lightly shaded, are added to the set C containing the vertex cover being created. Edges AB, CE and CD, shown dashed, are removed since they are now covered by some vertex in C. Part C in the above figure shows the edge E, F is chosen. Vertices E and F are added to C. Part D in the above figure shows the edge D, G is chosen. Vertices D and G are added to C. Part E in the above figure shows the set C, which is the vertex cover produced by approx vertex cover, contains the 6 vertices B, C, D, E, F and G. Part F in the above figure shows the optimal vertex cover for this problem contains only 3 vertices B, D and E. Theorem: Approx vertex cover is a polynomial time to approximation algorithm. Proof: we have already shown that approx vertex cover runs in polynomial time. The set C of vertices that is returned by approx vertex cover is a vertex cover, since the algorithm loops until every edge in G and E has been covered by some vertex in C. To see that approx vertex cover returns a vertex cover that is at most twice the size of an optimal cover, let A denote the set of edges that line 4 of approx vertex cover picked. In order to cover the edges in A, any vertex cover, in particular an optimal cover C star, must include at least one endpoint of each edge in A. No two edges in A share an endpoint. Since once an edge is picked in line 4, all other edges that are incident on its endpoints are deleted from E' in line 6. Thus, no two edges in A are covered by the same vertex from C star, and we have the lower bound modulus of C star greater than or equals modulus of A, and the size of an optimal vertex cover. Each execution of line 4 picks an edge for which neither of its endpoints is already in C, yielding an upper bound, an exact upper bound in fact, on the size of the vertex cover returned, modulus of C equals 2 modulus of A. We obtain modulus of C equals 2 modulus of A, which is less than or equals 2 modulus of C star, thereby proving the theorem. Let us reflect on this proof. At first, how we can possibly prove that the size of the vertex cover returned by approx vertex cover is at most twice the size of an optimal vertex cover, when we do not even know the size of an optimal vertex cover. Instead of requiring that we know the exact size of an optimal vertex cover, we rely on a lower bound on the size. The set A of edges that line 4 of approx vertex cover selects is actually a maximal matching in the graph G. A maximal matching is a matching that is not a proper subset of any other matching. The size of a maximal matching is a lower bound on the size of an optimal vertex cover. The algorithm returns a vertex cover whose size is at most twice the size of the maximal matching A. By relating the size of the solution returned to the lower bound, we obtain our approximation ratio. Conclusion: in this chapter, we have covered the following in detail: vertex cover, the traveling salesman problem, approximate algorithms, scheduling problems, set cover problem, bin packing problem, polynomial time approximate schemes, basics of parallel algorithms, Flint's classification, SIMD algorithms for simple problems, list ranking, basics of randomized algorithms, GCD algorithm.